Hi everyone, welcome to our senior project webpage. We are the Inverted Fluorescence Microscope team, otherwise known as Team.
Our project was brought to Cal Poly's Mechanical Engineering Department by Professor Hans Mayer and Benjamin Hawkins, director of the Microfabrication Laboratory here on campus.
For the academic year of 2019-2020, we had 3 tasks: to follow the engineering design process, to research and understand the operation of an inverted fluorescence microscope, to produce a design using readily sourced components in manufacturing processes, and to test and deliver a verification prototype to meet our engineering specifications at a cost lower than commercially available alternatives.
The microscope is operable in 2 modes, bright field and fluorescence. Standard bright field illumination is used to locate the sample and focus on the desired sample features, and fluorescence mode is used to acquire more detailed information about specific features of the sample by tagging these features with a fluorescent dye. For example, a microscope user can utilize fluorescence to track fluid particles through a small microfluidic channel or to label a fluorescent protein in a cell.
In fluorescence microscopy, the indicator dye in a sample excites at a specific wavelength and emits fluorescence at a slightly longer wavelength. Our design imparts fluorescence using an LED and captures it with an emission filter and a camera. Here's an animation of the path the light follows in a standard fluorescence microscope. Our design differs slightly as the sample is located above the objective instead of below, and utilizes a single wavelength LED instead of a filter to select excitation wavelength.
Our design process involved optical system component selection and design for both microscope operation modes, staged bracket design for actuator positioning and spring return along each axis, and electronic actuation of the microscope stage in order to maintain precise and repeatable sample locating.
We fitted an XY stage we purchased online with PLA brackets to facilitate linear actuation of the stage and a spring return mechanism to bring the stage back to its original position. Stage maneuverability is achieved using 2 linear actuators controlled by an Arduino.
We use SOLIDWORKS to model our system, determine component tolerances to meet our design specifications, and provide our sponsor with rigorous comprehensive assembly instruction. For the fabrication of our stage brackets, as well as some of the optical mounting and frame components, we employed additive manufacturing, making use of a 3D printer available to us in the microfabrication lab.
During spring quarter, we held weekly scheduled remote assembly sessions with our project sponsor to complete partial assembly and testing of our verification prototype in bright field mode, using our CAD model to supplement verbal instruction. Once again, we are Team. I'm Trevor Brown.
I'm Eduardo Miranda.
I'm Enoch Nicholson.
And I'm Mackenzie Kamei. Thank you. We're glad you're here.